Okay, let's move on. So in the next few papers, we are gonna forget about attention for a while. Let's see whether we can get away without attention. So whenever you want to know if something is important, just remove it and see how much you lose. So let's try to do that. It's an assignment for you to watch this video, but let's go into more details. Or actually, I'm going to give you an overview and then you can ask questions. So we removed attention. We want to translate ABC and the end of sentence to WXYZ and the end of sentence. Going back to your question, how do you actually translate when it comes to inference? You have this sentence, you encode it in a single vector. This last arrow is the representation of your sentence. Given the last word in your input, which is the end of sentence, predict the first word. That we can do. Take that, put it as input to the next step, bring in the history, and then go to the next step. Predict the next word. Take X, put it here, predict Y. Take Y, put it here, predict Z. Take Z, put it here, and as soon as your algorithm decides to output the word end of sentence, you put a dot. It means that the sentence is done, translation is done. And we are going to use a simple RNN to model both of them. The only catch is here, we are going to use deep LSTMs. And what do I mean? LSTMs are already deep. What do you mean? LSTMs are deep. They are deep in time. Here you are stacking multiple of them on top of each other, and you're going deep in space. The other trick is reverse the order of the words. And later on, when we actually do attention, we see that there is no need to do that. Or there is actually no need to do that if you have a bidirectional LSTM, an LSTM that goes from right to left, and then another one that goes from left to right. The input sequence, you know it, so just use that information. And then the next one is using beam search. The reason I'm going through this paper is to appreciate the amount of effort that people were putting into neural networks to beat the state of the art. This is the baseline system. This is the Moses algorithm. This has nothing to do with deep learning, and that's giving you this number for machine translation. And this is actually what Google was using up until around 2014. So if you were using Google Translate around or before that time, you wouldn't be that happy with the performance of the translation system. But these days, it's really good. So that's your baseline system. The paper that we just covered is giving you this as the blue score. So there is a huge gap to not using deep learning, just using classical machine learning techniques. But then this paper is doing everything that it can to beat that state of the art. And in the end, an ensemble of 5 reversed LSTMs, which is basically you're using, rather than using ABC, you're using CAB as your input. And a beam size of 12 is at last beating the baseline system by a small margin. But then there are some other state of the art at that time. There is also another idea. Rather than using beam search and using your neural network on its own independently, what if you want to complement the baseline system somehow? Let's take the outcome of the baseline system. It's going to give you 100 translations. Look at those 100 translations. You know the input sentence. You know the outputted sentence out of the baseline system. Take those 2 sentences, put them in your probability that is coming out of your neural network. That's going to give you a score about the goodness of this translation. And then sort those translations according to this single number, according to this score. And that simple modification is going to give you 36 in terms of your blue score. Blue score, the higher is the better. And to give you a perspective of how good you need to become in the end, if you have your baseline system translate a sentence, it's going to give you 1,000 candidate sentences. Show those 1,000 candidate sentences to a human being. They're going to sort it according to their own preference. That's going to give you the maximum blue score possible out of that exercise. So there is still a huge gap to human performance. And these are qualitatively some of the translations that are coming out of this process. So they are much better. Any questions about sequence to sequence learning? So if you hear the word Sick to sick, SEQ, and number 2, SEQ. That's this paper. Any questions about it? Okay, awesome.